Hello everyone. Thank you for joining us. In today's webinar, we will introduce our 3D electromagnetic simulation solution inside Autodesk Inventor. Our solution specialist will talk about different magnetic problems that can be simulated in our software. In addition, the webinar will include the demonstration of software workflow and simulation outputs that can be achieved using EMS for Inventor. Before discussing today's agenda, let me introduce us. My name is Cal and I handle sales and marketing division of our company. My colleague Arvind is a director of product management and an expert on application topics within the domain of low frequency electromagnetics. He will be delivering the technical part of today's webinar. Before moving on, I would like to highlight few points. During this course of webinar, if you have any questions, please feel free to use the chat window to type in your questions. We will answer them at the end of this presentation or will reply to you via emails. A webinar recording link will be sent to all the registrants in few days. Our agenda for today is following. I will briefly talk about our company EMWorks and the different package options available within EMS for Inventor software. Then my colleague Arvind will present the technical part of today's webinar. At the end of the technical presentation, I will talk about various learning resources offered by EMWorks for its software users. EMWorks offers 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in the year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. We have 2 office locations. Our headquarters is in Montreal, Canada, and we have another office in Germany. EMS for Inventor offers electrical and magnetic solvers. In addition, multiphysics add-on such as thermal analysis is also available with this product. This software is available in 3 package options: electric, magnetic, and professional. Arvind will talk about magnetic solvers during the technical presentation. Let us briefly touch upon the licensing structure offered by EMWorks. We offer 3 different programs: commercial, academic, and startup. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the 2 programs, our licensing structure is usually annual based. The topic for today's presentation is magnetic simulation inside Autodesk Inventor. My colleague will discuss 3 magnetic problems: busbar, solenoid, and a permanent magnet device. I would now request my colleague Arvind to take over and present the next part of this webinar. Thank you.
Thank you, Kalyan. My name is Arvind Krishnan and I'll be handling the technical part of this webinar. In this technical presentation, I will be showing you 3 different applications. The first one will be a solenoid valve where we will compute the force acting on the plunger for various positions of the plunger. The next application involves permanent magnets where we will study a permanent magnet device and understand the force acting on the block. Finally, we will use a collection of bus bars and simulate it under a short circuit current. Now, let us look at the solenoid application. Here is a cross-section view of the solenoid we will study. I have the plunger here in black. We also have the coil and the core that is supposed to act as a channel for the magnetic flux distribution. EMS is an add-in product to Inventor, so when you install EMS, you will be able to carry out the simulations right inside Autodesk Inventor. Here, I've created a study which is a magnetostatic study, and we have also exploited the parametrization feature inside EMS for Inventor. The parametrization feature allows you to parameterize any dimension, for example, the position of the plunger. Once the study is defined, we can take a look at how to define materials for the various components. Here, EMS Material Browser allows you to create your own materials or use the existing materials provided by the program. Here, we have a nonlinear materials. For example, we have used steel 1008. I can study the BH curve and all the other properties. In this particular example, the core and the plunger, they are both made of steel 1008. The coil is made of copper, and then there is also an air geometry surrounding the model. Once the materials have been defined, let us go over to seeing how to define a coil in EMS for Inventor. First, we select the components that comprise the coil. Then we also select the cross-sectional face as highlighted in blue. We can mention the number of turns and the current that is carried by each turn. Also, EMS allows you to specify the wire gauge of the copper wires that are used to wind the coil. EMS also allows you to calculate forces on ferromagnetic components. Here, we would like to compute the force on the plunger. Finally, let's take a look at the parameterization feature of EMS. Now, I have created a variable called travel that manipulates the position of the plunger. And in this parametric simulation, we have given 4 different values to that length parameter called travel. So we are going to have a travel which moves the plunger from 0.35 inches and then moves it up so all the way till the distance is 0.05 inch. Now let us take a look at the results. EMS allows you to look at the results using the result table. Now, in the result table, you will get the value of force. In this case, the value in the y-axis is about 0.048 newtons. You will also get the value of the inductance. This is for a scenario where the plunger is at a distance of 0.35 inches. We can easily change the scenario. For example, let's go to scenario 4 where the plunger is at a distance of 0.05 inch. We can take a look at the force. Notice that it is 0.18 newtons, and you can also look at the new inductance value. EMS allows you to visualize the magnetic flux density as 3D plots. Here I have a section plot of the magnetic flux density on the plunger. Notice the areas in red, and from the color chart you can read the value of the magnetic flux density in Teslas. The red values represent close to 0.6 Teslas here. This is the first scenario where the separation gap was 0.35 inches. I can also create these plots for various scenarios. Here, this was the final scenario where the separation was only 0.05 inches. So the plunger has moved up in this scenario, and you can read off these red values, and now they represent 0.85 Teslas. So you can see how the magnetic flux density increases as the plunger moves up. As a recap, let us understand how the variation of the force and the inductance happens. Now, I've highlighted the plot of the force versus the travel. So we had a travel of 0.35 inch separation all the way to 0.05 inch separation, and you can see that the maximum force occurs when the separation was 0.05 inch, and the force reduces as the separation increased, and you can see the plot of the force versus the travel. Here in this plot, I've also plotted the inductance in Henry versus the travel. In the next example, we will study a permanent magnet device and see how it can be used to lift a small block. We can also compute the force of attraction of the device and the block for various separation distances between the block and the device. Let me just quickly go to the first front view so that you can see how the separation distance looks. Now this separation distance is modeled as a parameter inside EMS, and then we can vary that parameter and study how the force of attraction varies with the separation distance. As before, we have created a magnetostatic study and we have selected the parameterization feature. Then we have applied the materials for various components. The back iron is made of steel. The two magnets, they are made of N42 material. The magnets are enclosed in a nylon casing, and the block is made of steel 1008. We also have an air geometry surrounding all of these. So let me just show the air geometry, and you can see the air geometry. I can go ahead and disable the visibility of the air geometry. In the EMS feature manager, the next thing that we would like to see is how to set the direction for the magnets. So here we can set the direction of the magnet using the coercivity direction command. EMS also allows you to look at the preview. For example, the arrow clearly specifies the north-south direction of the magnet. EMS allows you to use either global coordinate system or create your own local coordinate system in Inventor and use them to specify the direction of the magnet. In this particular case, in the left magnet, I've used a direction along y-axis. Similarly, on the other magnet, I've used the direction along the negative y-axis. So together, the two magnets and then the back iron and the block form the magnetic circuit. Because there's a separation between the magnet device and the block, there's going to be a force of attraction acting on the block. We would like to find that force. In EMS, we have requested the program to compute the force on the block for various scenarios. Now let's take a look at the scenarios. Now I have a distance mate where the value is controlled by this dimension D16 in Inventor, and I have assigned various values for this separation all the way from 0.05 inches to 0.25 inches. So we have 5 scenarios, and we will take a look at how the force varies and how the magnetic flux distribution varies across these scenarios. Now we can look at the result table and find those values of force. In this case, the force acting at scenario 1 is about 12.87 newtons, where the separation is very less, 0.05 inches. Now as the separation increases, for example in scenario 5, when you have a separation of 0.25 inches, the force is much lesser, close to about 2.15 newtons in the y-axis. EMS also allows you to look at the magnetic flux density plot. So here I have a magnetic flux density plot. In a section view, I can go ahead and show my air geometry and then double click on the plot again, so I can look at the variation of the magnetic flux in the solid components as well as in the air in and around these components. The red values and the yellow values can be read off from the color chart here, and you can see that the red values represent close to around 1.58 Teslas and the blue is low magnetic flux density. One can also take a look at a vector plot. Now this gives you the vector plot of the magnetic flux density when the scenario is 0.05 inch separation. I can go ahead and change the density and the size of the vectors so that you can see them more clearly. Similarly, one can even study the vector plot of the magnetic flux density when the separation is large, in this case 0.25 inches. I can again go back to the vector plot options and change the density so that one can see these vectors. Finally, EMS has the ability to create what is called as a 2D plot. Here I have 2 points set up in Inventor, and I can go ahead and create a 2D plot to compare and see how the distribution of the magnetic flux density varies from point 1 to point 2. So here is a curve that shows the variation of the magnetic flux density from point 1 to point 2. Now these points are work points created inside Inventor. As a recap, let's take a look at how the force varies as a function of the gap distance. So we started from 0.05 inch gap all the way to 0.25 inch gap, and you can see how the variation of force happens. So as the gap increases, the force acting on the block decreases. In this final example, we will study how EMS can be used to study bus bars. Here in this example, I've got an air geometry which I'm going to hide, and then I've got 3 sets of bus bars, and in each face I have 2 bars. So the first 2 bars are maintained at a different phase compared to the other 2 bars. So we have a 3-phase arrangement of bus bars, and the objective of this simulation is to study the force acting on the middle bars due to the short circuit current that occurs in all the bus bars. And we will also study the temperature distribution in each of these bars due to the short circuit current. As before, we have created a study, but this study is called a AC magnetic study because the bus bars carry AC current. They carry current at a frequency of 50 Hz. EMS also has the ability to couple to a thermal simulation. Here we would like to understand how hot the bus bars get. Next, we applied materials to each of these bars. The bars are made of copper, and then there is also an air region surrounding these bus bars. Then we will have to apply the current in each of the bars. So the first 2 bus bars carry a short circuit current of close to 6000 amperes, and then the phase is 0 degrees. The middle 2 bus bars carry the same short circuit current 6000 amperes, but they are at 120 degrees phase difference between the first 2 bus bars. And finally, the last 2 bars carry again 6000 amperes, but the phase shift is 240 degrees from the first 2 bars. We also would like to compute the force acting on the middle 2 bus bars. Now this is the dialog box that requests the EMS program to compute the force acting on the middle bus bar, the top one, and then similarly we would like to compute the force acting on the bottom bar. Finally, as far as thermal simulation is concerned, we would like to set up a convection boundary condition where all the bus bars are exposed to the air around it and the bars are convecting to the surrounding air. So we can read the force values in the result table. For example, the force acting on the top bus bar, the middle one, but the top of the middle bus bars um, is close to around minus 26 newtons. And then the force acting on the lower, the second bar of the middle set of bus bars is plus 26 newtons. Now you notice that these forces act in opposite direction, and we need to make sure that the distance separating these two bus bars are able to accommodate these short circuit current, which creates this enormous force. In addition to the force, EMS also computes the inductance matrix, it computes the resistance matrix, and finally the losses that happens in each of these bars. As far as the plots are concerned, it's nice to be able to visualize the current density plot so that you can see how the current distribution happens in these bus bars. Notice the plot of the current density vectors going through each of these bars. Now this high current is what is going to produce some kind of heating in these copper bars. Now finally, one can study the distribution of temperature in these bus bars. So you can see that due to this short circuit current of 6000 amperes, close to 900 Fahrenheit of heat is generated in these bus bars. So they need to be cooled, and you can also tell that this is kind of very high temperature, almost close to the melting of copper. So these three examples gave you a good idea of what is possible inside EMS for Inventor. Over to you, Cal.
Thank you, Arvind. Let us take a quick recap on our product EMS for Inventor. This product offers electrical and magnetic solvers. In addition, if you require to compute temperature distribution in your model, we offer thermal analysis add-on as well. EMS software is available in 3 package options inside Inventor: electric, magnetic, and professional. To get information on software pricing, you can connect with me after this webinar. We have some fantastic year-end offers, so do not miss out. This slide represents a small subset of capabilities available in EMS software. I will give a brief overview of 3 main capabilities. Number 1, magnetic and electric solvers. Magnetic solver can help a user to analyze magnetic fields, forces, eddy currents, losses due to time harmonic currents. An electric solver allows you to analyze electric fields, conduction currents, safety factor, breakdown voltages due to time varying or stationary electric fields. Number 2, thermal analysis. Through this multi-physics add-on, you can calculate temperature distribution, temperature gradient, and heat flux in your model. Number 3 is parametrization. This capability enables a designer to run multiple what-if scenarios to determine the best design. Coming to the learning resources, we offer various free learning tools. With the software purchase or an evaluation license, users can access the demo viewer section of our software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our webpage and social media channels regularly. We also offer paid customized training sessions to all the users of EMWorks software. Anyone interested to get more information on our products, including a trial license, quotation, can go to our Contact Us page on EMWorks website. Select the appropriate category, fill in your information, and submit your request. One of our representatives will reach out to you soon. I would like to thank you all on behalf of EMWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on this product. Thank you.